Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
1880 Willard, Gibbs on the Equilibrium of Heterogeneous Substances, Part D. The history of science occasionally produces a work of such profound abstraction and comprehensive scope that its full import remains latent for decades. A seed of pure intellect awaiting fertile ground. Josiah Willard Gibbs' monograph on the Equilibrium of Heterogeneous Substances, particularly its second and final instalment, published through 1878, stands as a supreme example of this phenomenon, appearing in the modest Transactions of the Connecticut Academy of Arts and Sciences. This sprawling treatise presented a complete, deductive, and mathematically rigorous framework for chemical thermodynamics, a discipline that before Gibbs was a collection of empirical observations and partial insights. This essay undertakes a direct evaluation of the internal claims, arguments, and specific conceptual frameworks advanced within the latter part of this monumental paper. It will proceed section by section through Gibbs' extension of his principles from the idealized realm of homogeneous fluids into the complex, tangible worlds of surfaces, strained solids, and electrochemical systems, assessing the logical coherence and revolutionary character of his proposals as they were originally presented. The analysis will reveal a mind operating at the highest level of mathematical physics, constructing a universal language for material equilibrium that would ultimately redefine the very foundations of chemistry and materials science. Section 1. The conceptual expansion to discontinuous systems. The second portion of Gibbs' treatise commences with a bold extension of the foundational principles laid out in the first. The central claim advanced here is that the fundamental equation, which expresses the internal energy of a system as a function of its entropy, volume, and the masses of its components, possesses the power to describe systems of far greater complexity than simple fluid phases. Gibbs puts forward the proposition that his criteria for equilibrium, namely the uniformity of temperature, pressure, and the chemical potential of each component throughout all coexisting phases, form a sufficient basis for analyzing phenomena at surfaces, within solids, and across electrochemical gradients. The evaluation of this claim rests on the sheer audacity and subsequent success of its application. Gibbs' method is one of pure deduction. He takes his initial abstract formulation, where the infinitesimal change in energy dE equals the temperature T times the infinitesimal change in entropy ds, minus the pressure P times the infinitesimal change in volume dV, plus the sum of the products of the chemical potential μ and the infinitesimal change in mass m for each component, and begins to add terms representing other forms of work and energy. This section serves as a methodological manifesto. Its core argument is that the edifice of thermodynamics, if built upon a sufficiently general foundation, can accommodate any physical reality through the precise mathematical definition of new energy terms. The strength of this claim is its absolute generality. Gibbs is building an architecture, a system of thought whose validity depends solely on its internal logical consistency. He spends the remainder of the publication demonstrating its immense structural integrity by using it to erect explanations for a vast range of physical phenomena. Section 2. The thermodynamic treatment of surfaces of discontinuity. Gibbs confronts the problem of the interface between two distinct phases, a region previously treated with descriptive, mechanical models of surface tension. His central and revolutionary claim is that a surface can be treated as a thermodynamic entity in its own right, possessing its own state variables of energy, entropy, and composition. To achieve this, he introduces a powerful and subtle conceptual device, the geometrical dividing surface. He posits a mathematical surface of zero thickness placed somewhere within the region of physical inhomogeneity between two bulk phases. The genius of this construct lies in its abstract nature. By defining all extensive properties of the total system and then subtracting the properties that the bulk phases would have if they continued uniformly up to this dividing surface, Gibbs creates a set of surface excess quantities. There is a surface excess of energy, of entropy, and of each chemical component. This claim is profound. It creates thermodynamic properties for a two-dimensional geometric plane. The evaluation of this argument reveals its complete logical soundness. Gibbs defines the surface tension, sigma, as the excess of the grand potential per unit area, and derives the fundamental equation for the surface itself. This leads to the famous Gibbs adsorption isotherm, an equation that relates the change in surface tension to changes in temperature and the chemical potentials of the components. He claims that the concentration of a component at the surface can be controlled by altering the surface tension, a direct and testable consequence of his theory. The intellectual rigor here is breathtaking. He sidesteps the intractable problem of describing the real, molecularly complex interface by creating a formal definition that is both exact and operationally useful. It is an act of pure theoretical physics, transforming a vague notion of capillarity into a precise chapter of thermodynamics. Section 3, the geometric representation of thermodynamics, throughout the work, but with particular power in the later sections. Gibbs advances the claim that the complete set of equilibrium states for a substance can be represented by a surface in a space whose coordinates are energy, entropy, and volume. The equilibrium between different phases, he argues, and be understood through the geometric properties of this surface. This is a claim about the power of visualization and geometric intuition in the most abstract of sciences. He demonstrates, for two or three phases to coexist in equilibrium, the points representing their states on this thermodynamic surface must lie upon a common tangent plane. The chemical potentials, temperature, and pressure are given by the intercepts and the slope of this plane. Evaluating this claim requires an appreciation for its dual nature. It is simultaneously a pedagogical tool of immense power and a profound statement about the underlying mathematical structure of thermodynamics. The consequence of this geometric insight is the celebrated Gibbs phase rule. He deduces with irrefutable logic that the number of independent variables, or degrees of freedom f, in a system at equilibrium is given by the expression f equals c minus p plus 2, where c is the number of independent chemical components and p is the number of coexisting phases. The evaluation of the phase rule finds it to be a pillar of chemical physics. Its claim to universality is borne out by its derivation. It depends only on the general conditions for equilibrium, independent of the particular substances involved. It is a tool of extraordinary predictive power, allowing chemists to anticipate the behavior of complex multi-component systems from first principles. The very existence of such a simple, elegant rule, derived from such abstract geometric considerations, served as a powerful validation of Gibbs' entire approach. It was a piece of pure mathematics that spoke a deep truth about the material world. Section 4, the equilibrium conditions for strained heterogeneous solids, perhaps the most formidable and intellectually dense section of the treatise, is Gibbs' extension of thermodynamics to solid bodies under mechanical stress. The primary claim here is that the chemical potential of a substance in a solid state, and thus its equilibrium with adjacent fluids or other solids, depends explicitly upon the state of strain within the solid. This was a radical departure from treating solids as simple, incompressible substances with a single pressure variable. Gibbs meticulously redefines the concept of mechanical work for a deformable solid. He introduces what amounts to the modern stress and strain tensors, though in his own careful, descriptive language. He argues that the work done during a deformation is the sum of the products of the 6 components of stress and the corresponding 6 components of strain. Consequently, the fundamental equation for a solid must incorporate these terms. From this, he derives a definition for the chemical potential of a component within a stressed solid. He claims this potential is a function of the stress tensor, meaning that a solid under shear stress, for instance, has a different tendency to dissolve or react than an unstressed one. The evaluation of this section reveals it as arguably the most prescient part of the work. Gibbs' formulation was so far ahead of its time that its full implications for metallurgy and material science would take nearly half a century to be appreciated. The logical chain is impeccable, by insisting that the definition of chemical potential as the change in energy upon adding mass at constant entropy and strain must hold universally. He is forced into these novel conclusions. He demonstrates, for example, why a crystal in equilibrium with its solution will dissolve at points of high stress and grow at points of low stress, providing a rigorous thermodynamic explanation for phenomena like pressure solution. The claims made in this section laid the complete theoretical groundwork for the modern science of solid-state thermodynamics. Section 5, the thermodynamic theory of the galvanic cell. Gibbs next turns his formidable analytical engine to the realm of electrochemistry. His central claim in this section is that the electromotive force, or EMF, of a reversible galvanic cell is a direct and measurable manifestation of the thermodynamic properties of the chemical reaction occurring within it. He proposed that the electrical work performed by a cell could be incorporated into the fundamental energy equation, just like mechanical work. The additional term is the product of the EMF, which he called the electromotive force E, and the infinitesimal change in the quantity of electricity that has passed through the cell. By applying the general condition of equilibrium, which requires the total change in energy to be zero for any virtual change at constant entropy, he derives a powerful relationship. He claimed that the EMF of a cell is determined by the decrease in the system's energy when the reaction proceeds, minus a term related to the heat absorbed from the surroundings. This is equivalent to stating that the electrical work done is equal to the decrease in what is now known as the Gibbs free energy of the reaction. The evaluation of this claim confirms it as a moment of profound unification in science. It connected the macroscopic, measurable voltage of a battery directly to the microscopic, abstract quantities of chemical potential. Gibbs' formulation implied that one could use a voltmeter to measure a fundamental thermodynamic driving force. He further analysed the effect of temperature on the EMF, deriving what would later be known as the Gibbs-Helmholtz equation. His claims provided a complete theoretical basis for understanding electrochemical cells, transforming the field from a set of empirical rules into a predictive, quantitative science. It was a stunning demonstration of the unifying power of his abstract framework. Section 6, the nature of osmotic pressure and semipermeable membranes. In the final portions of his treatise, Gibbs addresses the perplexing phenomenon of osmosis. His core claim is that osmotic pressure is not a special, mysterious force related to membranes but is a direct and necessary consequence of the universal principle of equilibrium of chemical potentials. He conceptualizes a semipermeable membrane as an ideal theoretical boundary, one permeable to the solvent but completely impermeable to one or more solutes. For a system containing such a membrane separating a pure solvent from a solution to be in equilibrium, he argues that the chemical potential of the solvent must be identical on both sides. The presence of the solute, however, lowers the chemical potential of the solvent in the solution. Gibbs claimed that to restore the equality of potential and thus achieve equilibrium, the pressure on the solution side must be elevated by a specific amount. This excess pressure is the osmotic pressure. The evaluation of this argument finds it to be an exemplar of his method's elegance and power. He explains a complex biological and chemical phenomenon without any specific model of the membrane or the nature of the solution, relying only on the first principles of thermodynamics. His derivation showed that osmotic pressure depends on the temperature and the concentration of the solute, providing a rigorous foundation for the empirical laws that had been discovered by others, like Van't Hoff. This section is a final, compelling piece of evidence for the universality of the chemical potential concept. It demonstrates that a single idea, rigorously applied, can illuminate phenomena across disparate fields, from the dissolving of crystals to the passage of water across a cell. Conclusion: the examination of the internal claims within the second part of Josiah Willard Gibbs on the equilibrium of heterogeneous substances reveals a work of unparalleled intellectual synthesis and deductive power. From the abstract creation of a thermodynamically defined surface to the rigorous extension of equilibrium principles into the complex world of strained solids, and culminating in the unification of chemistry and electricity, Gibbs' arguments are consistently logical, coherent, and revolutionary. He claimed nothing less than the existence of a universal mathematical language capable of describing all states of material equilibrium. The evidence he provided was the construction of the language itself and its successful application to problem after problem, each solved with an elegance and finality that left little room for doubt. The evaluation shows that his claims were not empirical generalizations, but the inescapable consequences of a few foundational postulates. His work did not merely add to the science of chemistry, it provided it with a new, unshakable logical structure, transforming it into a deductive science on par with Newtonian mechanics. The true significance of the treatise lies in this profound methodological shift. Gibbs demonstrated that the most complex behaviours of matter could be understood and predicted through the austere beauty of mathematical physics, creating a framework whose full, colossal implications would continue to unfold for the next century and beyond.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.